Today, I'd like to talk about issues that you need to notice in model development. When we train a model and we need to find which model would be the best to select, basically, we train a model with a set of parameters or a grid of parameters. So, which one should we select? Here we based on the generalization error. In supervised learning applications, the generalization error, also called the out of sample error, is a measure how accurately an algorithm is able to predict for unseen data. And this is according to Wikipedia. The generalization error can be decomposed into bias and variance. The bias basically is the average error for different training sets, and the variance measures the sensitivity to varying training sets. On this slide, taking MSE, which is mean square error, as the measure for error. In the formula, y is the target, the true target, and y hat is the estimate of y. We can decompose MSE into bias of y hat squared plus the variance of y hat. So looking at the formula, we can see that bias actually measures the error of estimation, which is the expected value of y minus y hat. And the variance measures the spread of the estimated y hat around the mean of y hat. When we talked about models, typically we have simple models. We have models which are just right and complex models. So we talked about model complexity. Model complexity may be in terms of degree of polynomial kernel, or if our model is a neural network model, then we talked about the number of hidden nodes. Or if the model is a decision tree or random forest, then we talked about the depth of a decision tree, or the base tree in a random forest model. Model complexity is also in terms of the number of neighbors in nearest neighbor methods. Now let's see what happens when we increase the level of complexity. Typically, training error decreases as complexity increases. However, generalization error has a U-shape. Looking at the total error curve, we can see that the error is high for models with low complexity, then decreases until we get a model which is just right. And then it is high again for models with higher complexity. Let's take the degree of polynomial as model complexity. With low model complexity, for on the left side, we can see that both the generalization error and the training error are high. And then the error decreases as the degree of polynomial or the model complexity increases. And at some point, we have the lowest error, the lowest generalization error. After the point, the training error keeps decreasing, but the generalization error starts increasing. So this point is where we need to get our model. A model with low complexity would mean high bias, and high bias would mean low variance, and vice versa. If we observed high cross validation and also high training error, then our model is basically high bias and it is underfitting. The model is more on the left side of the curves. If instead we observe high cross-validation and low training error, then that would mean our model is high variance, it is overfitting, and it is more on the right side of the curves. Models with low complexity typically tend to underfit the data. This is because it is not sufficiently flexible to describe patterns in the training data. On the other side, models with high complexity typically overfit the data. This is too much flexible, so it fits to noise in the training data also. So the models would not generalize well. Now we talked about several ways to avoid overfitting. Reusing the same training data set for evaluating a model would be introducing overfitting. The model would learn very well about the training data points, but then doesn't work well with unseen data. And this is called resubstitution validation. We use the cross-validation technique to find the optimal model, which balances bias and variance, and at the same time fixes overfitting. We will talk about the holdout validation, k-fold cross-validation, and leave one out cross-validation. The holdout method basically probably is the simplest kind of cross-validation. We split the data set into two sets called the training set and the testing set. We then fit the model using the training set and then later on predict using the testing set. In practice, a variant of this method called the three-way holdout method is used commonly. Typically, the data is split into three different sets: the training set, the validation set, and the test set. The training set is used to train the model, and the validation set is used to tune the parameters. The test set is set aside to assess the performance of the training classifier. After you run the test set with the model to see how the model would perform with unseen data, you should not tune the model further, and this is important. Typically, we try a number of parameters and store the one that performs best in terms of a cross-validation error or generalization error. Here are some examples for partitioning data. You may have 60% for training, 20% for the validation, and 20% for the test set. In another example, we have 70%, 15%, and 50% for training, validation, and test sets. And finally, in the last example, we have 8%, 10%, and 10% for training, validation, and test sets. In the k-fold cross-validation approach, data set is divided into k subsets, and then we repeat the holdout method k times. In each time, one of the subsets is used as a test set, and the rest, meaning k minus 1 subsets, are used for training your model. Then afterward, we average the error across all the k trials. The advantage of this method is that we have more data for training, and there will be less matter on how the data is split. So more data used for training would mean like each example or data point is in the training set k minus times, and still the separation between the sets are maintained. We can control the variance of the estimate. When we increase k, the estimate variance is reduced. However, this approach comes with an disadvantage. because the tuning algorithm runs k times, so this is very expensive interval computation. A variant of this approach is that the size of the tuning and the test set vary in the k trials. The leave one out cross validation approach basically is the special case. The number of folds basically is the number of data points in the set. So this approach is very expensive computationally. In general, the k-fold cross-validation and leave one out cross-validation methods are better than the hold-down method. In the hold-down method, we have fewer examples for tuning because we have to save some for cross-validation. We're splitting into k-folds. Each example is used in the tuning, so that's where and why we need more data used for tuning.